Hello everybody, thank you for coming to my talk about Dvb T hacking. Just before we start, a bit about myself. So like she said, my name is Amichai Neiderman. I'm a security researcher from Israel. And after hearing the last talk, no, I'm not a spy, don't have any strong political beliefs or ideology. I work as a security researcher at the head of research at a small company called Equas Technologies near Tel Aviv. I mostly do vulnerability research for fun at home and at work. So let's just start. Now, let's see if it clicks. What exactly is Dvb T? Now, Dvb T stands for Digital Video Broadcasting Terrestrial, which is just a standard for digital television broadcasting, and it replaced the old analog standard that we used to have. So if you remember those antennas that you see here on the rooftops, or this, then it's gone. What we have today are receivers like this, and the way it works, you go to the store, you buy a receiver like this, they're pretty cheap. You plug in an antenna and plug it into your TV, and you have digital video broadcasting. Now, in Israel we have about 4 channels. It's not very popular, but we do have some. But once you buy it, it's pretty free, so it's cool. Now, the name of the network in Israel, it's called Idan Plus. So if you hear me using this name during the talk, then just for you to follow. The receiver, like I said, are pretty cheap. They cost about $50 US. And one of the most popular one is the Silverline H26113NB, and it's made by a Chinese company called M-Star and sold by a different company in Israel. It's just a sticker brand. Now, what actually brought me to research Dvb T? I really like researching IoT devices. It's pretty fun. You find really nice vulnerabilities that you can exploit in a day or two. And I really like it. I love it. It's like my hobby. But lately it seems that all the routers in the world were written by the exact same person, because you can find the exact same vulnerabilities over and over. It's the exact same ones. And I really love my TV. I have a smart TV. I thought of trying to mess around with it, but it's pretty expensive. I thought of messing around with those smart refrigerators, but I don't know a single person that have those. And I would really like to research them, but I don't know somebody with that. And finally, it's pretty cheap. The receivers, like I said, are really, really cheap. So I just went to the store, asked for the cheapest one that they have, and it was luckily the most sold one. And this is what they gave me. This is the exact same one. Now, for those of you who were in my talk yesterday, I usually work with a simple plan with usually like 3 steps and evolve it as I go, something like 1, 2, 3 profit. I won't be doing this today though. I'm going to give you the outline of my plan. So I had one goal in mind. I really want to hack this Dvb T receiver, and preferably over the air, because radio frequency is fun, RF is fun. Everybody are hacking stuff over TCP now those days, and I want to do something different, something that people don't usually do. So in order to hack it, I first have to get the firmware. Now I need to find the correct firmware, the right version. I need to reverse it for a while, spend a few hours working on this, open the casing, get electrocuted, like it's a risk that you get shell access, reverse some more, find a bug, exploit the bug, and yay. And yay is actually giving a talk here in Romania, which is pretty cool. So I started with getting the firmware, and there are basically 2 main ways to get a firmware for a device you're trying to research. The first one is downloading the firmware update, either from the manufacturer site or from some bizarre Chinese website, or you could extract it from the device itself. I tried looking at the manufacturer site, but I only found outdated versions or localized ones. And I didn't find anything pretty interesting in those Chinese websites. What I did find was this. Those, I'm not sure if you can see it. It's leaked M-Star CPU schematics. That's the same CPU that they're using in the receiver that I bought. And it's a MIPS CPU, so you need to remember that. It's a MIPS architecture. And if we take a closer look, you can see here in the red, there are 2 lines coming out, labeled UART TX and UART RX. Now, UART is just a serial connection, so there's probably a console we could connect to, And using this console, we might be able to extract important files, maybe the firmware itself, and now we'll have something to research. So let's get us some shell access. So I started by opening the case, and you can actually see right away that there is a lot of waste space in the case. They could make it like 3 times smaller and much cheaper, so all of this place is just a waste of money and metal. And if we take a closer look, we can start identifying some of the parts. So the first one, don't touch this. If you open one of those, you get electrocuted. Not kidding, it happened. This is the CPU. It's pretty easy to spot because of the large heatsink. Here we can see the serial connection. We can enlarge a little bit. And there are some other small parts that you can see around here scattered on the circuit board. And it was a bit hard to identify them, so I needed to find a better way to get a look at them. So I bought this really cheap microscope from Deluxestream and took some close-up pictures. And here you can see, well, it's hard to see from here, you can see the flash chip. You can see some writing on it, so I was actually able to identify the exact vendor and brand and version of that specific chip, and it will help me later on. And after doing all of this, I was able to build this basic block scheme for the device itself. So we have the CPU, it's connected to a USB on the go, it has 64 megabit serial flash and 2 DDR RAM memory. So I took apart the circuit board, and this is actually me soldering. You can see a piece of my leg here. You can see me soldering the wires to the serial connection. And like I said, if I'll get a serial connection, maybe there is a console, and maybe I could extract some of the files for me to research. So I managed to identify which of the pins is which is the TX, RX, and ground. It was pretty simple. But I still need a way to read the data from it. And I bought this fake FTDI. What this thing basically does, it just translates serial UART data to USB and vice versa. It's pretty cheap. If you're into hardware hacking, you want to get into it, costs less than $10 on eBay. It's a must. And after doing this, I had this pretty cool setup at home. Like my wife isn't here, so I can say I'm not sorry for the mess and bringing people to see like how cool is this. So you can see my computer connected to the box itself. You can see the FTDI and the serial connection running on the carpet. And after having this setup, I booted up the device. And here you can see it prints a lot of data to the screen, prints some data about the board itself, about the bootloader, prints some memory addresses. And I waited for a few minutes for the shell to pop up. And after about 2 minutes, all I got was just an endless loop of this string. It says, know this country in EAT. I have no idea what it means. And it wasn't quite what I was expecting for. I was expecting something more like here on the left, like a real shell access, a Linux shell. And it wasn't what I got. So I took the different approach, and I had to extract it from the flash chip itself. So like I said, I was able to identify the exact brand of the flash chip, and I went to the manufacturer site. Here they had a pretty good documented data sheet, and I downloaded it from their site. I had the functional block diagram, so now I knew what every leg on the chip does. And I also learned that it's using SPI as its communication protocol, which is pretty cool because I could just take my Arduino. Somebody already implemented an SPI library for Arduino. I took the circuit board and I did it the lazy way. I know it could make electrical engineering mortified, but I took the circuit board and I didn't really want to take the flash chip out because if I'll take it out, I was pretty sure I won't be able to solder it back in. So I found the part on the circuit board where the legs of the chips coming out from the plastic on the back side of it and soldered wires to it. I know it's the worst practice you could do, but it worked. So I'm not sorry about that. And somebody already implemented this specific chip protocol. So I just put everything on my Arduino, told it to dump all the data from the flash chip, and after some work, some tedious work, I got a working framework, which I can actually start reversing now. So this is an actual picture from my IDA. That's, I think, the entry point. It's not that interesting. So I reversed it for a while, and those are my nodes. So it's running ECOS, which is, anybody heard of it here? ECOS? Nobody, all right. Weird. So it's just an so it's just an embedded operation system for for embedded devices. It took me about a couple of hours to understand that it's an open source after I reversed some function of it. It has no shell access. Nobody compiled any shell into it. And on the CPU itself, there are no debugging options enabled, not even an EJ tag that you can find on a lot of different MIPS CPUs. This specific one, they tried to make it as cheap as possible, so it didn't have any support. And there is a lot of code on it. I mean, there is a lot of code, and reversing it statically, it's going to take a long time. And it was meant to be like a fun summer project for me. I didn't want to work hard on it. And I really need the debugger, because when you have a debugger, you can say, well, I'm going to jump over this function. I'm just going to check what the outcome. So I thought, well, I really need a debugger. What should I do? And then my wife, she really loved this show. She said, well, what will MacGyver do? He's probably going to build a debugger. So I said, well, I'm going to build a debugger myself. And I made a list of what a debugger should be able to do, because I've never done it before. And the first thing I thought of is inserting breakpoints. It's like eBFE on x86, like an endless loop. It's something that it's a must, and it's really important for when trying to debug something. So the debugger should be able to insert breakpoints, should be able to read and write to map memory, it should modify the program code, it should read CPU registers, should be able to do single stepping, like it's a luxury, but maybe it's something it should be able to do. And the debugger should be able to talk to a debuggy, which is an actual problem here, because the debuggy is a box sitting on my table, and it's not a program like I'm used to on my computer. Now, with that in mind, I thought that the debugger should be made out of two parts, like a lightweight server that runs on the box itself, and a client side that's running on my laptop that does all the complicating processing, holds the state machine, and that's what I thought it should be able to do, but still there's a question of how they're going to talk to each other. Now, if you remember the setup that I had, this one, then my laptop is going to be the client, the box is the server, and I know there is a serial connection. I could use it to communicate between the client and the server. Now, I know I can read data from it, because I managed to read all the data that spills during the boot process. Maybe you can also write data to the box itself, because there is what I think an RX port on the receiver itself. But I still need to prove this before writing the debugger itself. So I started reversing the easiest part I could find, and it's called mboot. It's a U-boot ripoff by mstar. I just took U-boot, changed some strings, but it's basically the same. And it says a lot of easy to understand code. It writes a lot of data. Maybe it's also reads something. And after reversing for a while, I found in one of the first stages, I found this function. And you can see here, there's this string on the first block that says, hit any key to stop the auto boot. Now, it's interesting because of two parts. The first part, I found a function, I call it myPrint. It's a function that writes data to the serial. And the second thing, now it waits for user input. And that's great. So I reversed some more, and I found this piece of code. And you can see here that's what it does. It reads data from a specific address, BF201328 hex, from the RAM memory. And when the lower bit is set on, it goes to a different address, not that far from it, and reads a whole word from it. And then return 1 byte. So this looks like reading from a serial from some memory mapped I/O, and this is actually the reading function from the serial connection. So now I know how to read and write from the serial, and it's time to write the debugger itself. So, like I said, breakpoint is probably the most important part in the debugger, And this could be done, you can implement breakpoint in different ways, depending on the architecture you're running on. On x86, you could use hardware breakpoints with specific registers. You could use JTAG on some CPUs. You can use special instruction like break instruction, or you can do jump patching, but it's pretty lame. I chose the break method. And for example, if you want to put a break instruction on this specific line, all you have to do is to replace the original instruction with a break instruction on MIPS. It's 0D hex. And copy the original data somewhere else, so you'll be able to restore it. And now whenever the program counter hits this specific line with the break instruction, then on MIPS you'll get an exception. And when you get the exception, then the program execution will move to this piece of code. And this is the exception vector handler. It's almost usually located on this address, 80,180,000. And what it essentially does, it takes the exception code, and it has a list of exception handlers. So exception on MIPS break instruction, it's exception number 9. So it goes to cell number 9, the exception vector, and check what is the handler for this specific case, and jump to this address. So if we put it to our server client design, if we hit the break instruction, then the execution will jump to our server code. The server will notify the client over UART that something happened, and the client will take it from there and decides what to do. Now, like I said, I want to make the server as lightweight as possible. And the best way I thought of making it lightweight as possible is that the server should only implement 4 primitives: reading a byte, writing a byte, getting a register, and setting a register. And if you remember the list I made from before, then I can show you that I can implement each and every of those requirements with those 4 primitives: reading, writing, getting, and setting a register. So, for example, if we want to put a breakpoint, all we have to do is the client have to send a request to read 4 bytes, and you can ask for 1 byte at a time, save it on the side, and then he writes 4 bytes that says break, and continue execution. This is how the pseudocode will look like. So you can see it just reads the original data and writes 4 bytes to the program. And whenever it encounters a breakpoint, it checks if the breakpoint, the exception actually, happened on the same address that we put a breakpoint on. And if so, then it restores the original data that was there, the same instruction, and continue execution. So I wrote the server pretty quickly, mostly in C, some assembly for the more low-level parts. The client was written in Python because it only makes sense because it runs my computer. But I still need to find a way to put the server on the box itself, because having it on my computer, it's nice and all, but doesn't help me a lot. So if you remember this piece of code, if you hit the any key, which is actually not any key, but a specific key that I don't remember which one, then you get a pretty sophisticated menu. It's a mboot, uboot menu-like, and it lets you, using the USB on the go port that they have, to upload any binary that you want into the memory of the device and run it. So I took the firmware that I managed to dump from before, patched the exception vector to point to my debugger server code that I just put at the end of the firmware, and added something called myControl-C and uploaded it to the device. Now, what exactly is myControl-C? Do you know that when you debug a program, you can press Control-C and it stops, and you can start messing around it with GDB, right? All right, right, I guess. So I really want to have the same ability to do this on the box itself. Now, there isn't a keyboard, but what I do have is a remote control. So I reversed for a while, and I found a function that's responsible for the volume up. When you press volume up on the remote control, then this function gets called. All I had to do is just place a breakpoint on it, and now whenever you press volume up, you get this on my computer. This is the actual debugger code running my computer. You can see all the registers, and you can start sending debug messages to it using this console. It's made of a mix of GDB and WinDebug commands, the one I like from each of those debuggers. and it worked. And now I can actually start working on what I want to do. So, like I said, I need to hack it. Like, I had another goal of building an embedded debugger because it was the first time for me. So I added something else, another thing. But it's time to find a bug. So what exactly is Dvb T? So I read the Etsy manual, and Dvb T is hundreds of highly technical implementation-related data. It's 4 pages of abbreviations at the start, graphs that I don't understand. Everything is called tables for some weird reason. I call them packets because it's easier for me to understand that in packet forms. And they're actually pretty documented. And somebody had to make a mistake when implementing this thing. The question is where? Now, this is the protocol by me. I tried reading the ETSI, the European Telecommunications Standard of Institute manual. Didn't understand a thing. I think they did it on purpose. They tried to write it in a language that nobody will understand. And I didn't understand a thing. So I wasn't really sure where to start. So I thought, well, maybe I could learn really good about Dvb T, I could really focus on it, and maybe I could find a soft spot, the place in the protocol that is prone to problems, but I need to learn really good about the protocol before doing it. Maybe I could start with the easy to parse packets, the simplest one. Packets means tables, if somebody actually understands the protocol here. Maybe I can find the easy to parse ones, and it will help me to gain better understanding of the protocol. I could go right away for the most complicated one. It will be more reversing work, hard reversing work, but somebody had to mess them up because it's a pretty complicated protocol. Or I can do fuzzing, because everybody does fuzzing now. So I started doing fuzzing, and I started by placing a low-level hook with my debugger, so it finally had to use it. On a packet that I call it packet receive, and that was the lowest part in the firmware that I found that actually talks to the radio device in the box itself, in the receiver. This is what actually takes the binary data that came from the air and send it to the other parts of the device. So I'll place a low-level hook on it, and now I can control the data coming from the device, because I can just change it to whatever I want, and I can do all the fuzzing attempts from my laptop. And it's easier than trying to transmit it using a USRP or HackRF or something like that, and way faster. I thought of using some generic fuzzer for the mutation generating. You only have to fuzz around 20 different tables, and all you have to do is to make sure that the CRC is okay at the end. And this is how a packet looks like. You can see there is a lot of binary data floating around. There's a CRC in the end. You just have to make sure it's legit. And you can see there's a lot of data to mess around with. Section in the syntax indicator, reserved something. So I had something to work with. So if you want to fuzz, you can just run this command and send it to the debugger. It will place the data. So what you see here is just a packet being sent, and it's changed and I only changed 1% of it at a time to make it like solid so it won't break things up. And this held for about 20 seconds. Because during the first fuzzing attempt, I started reversing the easiest function packet I could find, and found this piece of code. Actually, this packet, the time offset table packet. And you can see here that it's pretty interesting because it has you can put as much as n different descriptors inside of it, and n is defined as the descriptor loop length. And it's the size of 12 bits. So you can put about 4,000 of those descriptors inside this packet. And if you look at how the descriptor looks like, then this is a descriptor. And you can see that the descriptor, first of all, doesn't have a CRC in it. That's interesting in the first place. And it has an n of itself that is derived from the descriptor length, which is only 8 bits. Now, you can send a pretty large packet this way, over the air. And when it came time to implement that, the writers of this specific code decide that n is always equal to 1 for some weird reason. So this is the descriptor. This is the struct of how it's supposed to look in memory. They decide that n is always 1, so instead of having a dynamic size, it's always a static size of 15 bytes, because who needs more data? And I honestly don't know what this descriptor has to do, what it does, but it's not supposed to be 1. And this is, we can say this is the code that they wrote. It's like a pseudocode of it. And they actually checked that the descriptor loop length is more than 0, but they're only trying to parse the first descriptor. But they're thinking that the descriptor is in a static size. So you can see that they allocate a struct on the stack itself in the size of 15 bytes for the descriptor, but they're reading a dynamic size from the myParse time offset descriptor function, because the internal function actually tried to send back a dynamic size for the descriptor itself. So you get a pretty basic stack overflow, pretty simple one. So now we found the bug, pretty simple one, and you can find the exact same vulnerability almost anywhere where they thought that who needs to have more than 5 antennas in an area, and they only allocate enough data for the amount that they thought that somebody will ever send. It's a pretty common mistake that they had all over the code, but this is the one I decided to exploit because of this piece of code. Did anyone here ever try to exploit a MIPS vulnerability on MIPS? No? All right. So if you ever try to do it, then you know that this piece of code says that everything's going to be okay. Because usually on MIPS, when you call a function, then you get the return address not on the stack like you have on x86, but on a specific register called array, the return address. But here, they actually put the return address on the stack. And we can control the stack because we have a stack overflow. So you can see here on the first block that we're reading the return address from the stack. So we can control the flow of the program. And this is what we want to have. And because it's MIPS and it's an embedded device, you have no ASLR, you have no NX bit. It's really fun, it's pretty simple to exploit. It's like exploitation 101, every tutorial that you ever took. And all we had to do is do something like a jump to SP. And on this specific CPU, they disabled the caching. So the instruction cache and data cache, the only real problem that you have on MIPS devices, the only thing that can actually destroy your exploitation, doesn't even exist here. So it's like the easiest exploitation that you can have. So it will look something like this. You just return to your shellcode that you know where it is. It's pretty simple exploitation. Worked in 2 minutes. I bought an AKRF a couple months ago. Had to smuggle it through the airport, and that was the first time that customs actually arrested me. But they looked for drugs that day, so they opened this thing, which is legal in Israel, checked that they don't have drugs in the box, and gave it to me back. The first time in hundreds of flights that they ever checked me. And you can see there's a lot of implementation online for GNU radio that help you send Dvb T packets or tables, or just stream over the air, and you can send this exact same vulnerability. I tried to do it on the lowest power I could do because I didn't want to destroy all the receivers for my neighbors. Now, this thing is pretty stupid. It doesn't do a lot. It can't transmit anything yet. So if you exploit this, then you can't actually know that you managed to hack somebody. You can start putting your own broadcast if you want. You can send your own commercials. You can make somebody's life miserable with that, but not more than that. But I'm actually starting to look at this. It's the new TV I bought, and it's connected to this receiver in my living room. And now you can actually start from this with an attack over the air. You can maybe attack this television, which runs Tizen operating system, which doesn't look very good for this time of being. Thank you very much.